Welcome to the second part of the T12 tutorial titled Underdetermined Wideband DO Estimation and Target Localization. So for this second part, I will talk about these two sections. Section 3, so Underdetermined Wideband DO Estimation with direct group sparsity, and Section 4 is Underdetermined Wideband DO Estimation exploiting frequency diversity. So now for Section 3, so we have 4 subsections. First is array model, and then we talk about the sparsity-based DO estimation for a single frequency, basically the narrowband case. And then we talk about how to extend this narrowband to the wideband case. So wideband extension based on group sparsity, and then I'll give you some simulation and the experimental results. So the array model. Okay, so first approach to underdetermined wideband DOA estimation is based on the co-array concept, exploring various sparse array structures, such as these co-prime arrays and nested arrays. So, and it's a direct extension of the narrowband approach from the single frequency to multiple frequencies using this group sparsity technique. And this extension is applicable to all sparse array structures. And we just use sparse array in this section as an example. And even for sparse array, there are different constructions, okay? And one of them, so is a typical one, so consists of 2 uniform linear subarrays with 2 M and N sensors respectively, and where M and N, they are co-prime. So here is a structure. So it's a general co-primary structure with unit spacing D. And so you see here, there's 2 subarrays. I show these 2 subarrays separately in 2 separate lines, just to make sure you can see this clearly. But actually, they are put along the same line, so it's a linear array. Okay, so this first subarray, you have N sensors. So, but the spacing between adjacent sensors is given by M times D. So MD. So you have sensor 0, sensor, so MD, 2MD, 3MD until to this N minus, big N minus 1 times MD. And for the second subarray, so we also start from 0. So you have ND, the spacing is ND, big ND, so 2ND, 3ND until 2 times M, big M minus 1 is times ND, okay? So you have these 2 subarrays with different spacing. And in total, you have this one, as you have N sensors, this one 2M, but they share the same sensor 0. So you can remove one of them. So as a result, in total, you have 2M plus N minus 1 sensors. So for this typical co-prime array structure, here is M is smaller than N. Just to see here, the ND, the spacing is larger than this MD spacing. So this second subarray is larger than the first subarray, the spacing. And the difference co-array, if you do the difference co-array, so then created by this structure can provide degrees of freedom of more than 2M times N. So with 2M plus N minus 1 sensors, you have a degrees of freedom of 2M times N, more than that. And assume, so again, so we have K uncorrelated wideband signals with the same bandwidth impinging from incident angles is state K so K from 1 to big K. Okay, so we have for this co-array concept to work, this idea, we need to assume the sources, they are not correlated with each other. Okay, and then the signals observed these two subarrays can be given by this. So this is a standard wideband data model. For the first subarray is X1 N, so nth sensor, and for the second is X2 M, so mth sensor. And you have this SK, so T minus tau 1 and theta K, that's the delay, the corresponding delay. And this is noise. Then, so you can, so do this analog digital conversion. So each received sensor signal. So after this, you got discrete time form of the data, and then you group them into different blocks. So each block you have a size of L, and then you apply this L point DFT to each block of data, and then this P is the block index. So L is the frequency, this frequency bin, DFT frequency bin index L. So you put this DFT results into this vector. This is for first subarray, second subarray, and here is the standard DFT operation. Okay, so basically you have a block of data with the size of big L. So P, you change the block index. Okay, here. And then you have this frequency domain, DFT domain, this data model. So the first subarray X1 LP, and you got this. This is a steering matrix for the first subarray, and then this is the source vector at this block index P. Okay, and this is noise. And the second, this is the second equation for the second subarray. So this steering matrix, and this is a steering vector for the first subarray, and this is for the second subarray. Okay, and then you put these two separate data models, right? You can put this X1, X2 together into one big vector. So consider this as a whole, as a single array. Then you put them into this vector, and then you can calculate the covariance matrix. Okay, so covariance matrix of this this whole array data, this model. Okay, then it's given by this, and the standard result you assume, because you have assumed they are non-correlated, so you have this sigma KL. This is the power of the signal at the frequency L, bin L. Okay, so sigma K squared, and this is the corresponding steering vectors. And here is noise, because noise is spatially wide, so you have this diagonal, and so diagonal matrix. We have assumed that so they all have the same power. Okay, so this spatially and temporally wide. The virtual array is generated by vectorizing this. So you do the vectorization, then you can generate this virtual array like before. So vectoring this, you use a ZL. So for this Lth bin, so ZL, and then you have this new steering matrix. It's virtual steering matrix. Okay, and this is the source vector. Okay, so you put this into this vector, and then you vectorize this. You got this structure. So this is I tilde this. This is the vector. Okay, so it's 2m plus n minus 1 squared times 1 column vector obtained by vectorizing this. Okay, and then apply this sparsity-based approach. So you have this search grade of this kg potential incident angles. So theta g0 until this theta g kg minus 1, and then you generate this overcomplete steering matrix or dictionary. Okay, so you have this big kg of the columns. Okay, And then you can construct a column vector S tilde G consisting of these KG potential source signals. So the KG elements with each of them representing a potential source signal at the corresponding incident angle. Then you can put this and the noise together. So put this noise and this overcomplete stereo matrix together, and also put the source vector, this overcomplete, source vector and the noise together, then you can have this model. So basically this one times this plus this one times this, and you got this received data, this virtual data, after vectorization. And then the sparsity-based DO estimation method, then for single frequency, so we can formulate this like this, in this way. So this is the L1 norm, and this is the, so this is reconstructed signal minus this observed. So you have this reconstruction error, and this error is so subject to this bound, this epsilon. You can choose this value, and then we know this when you do this L1 norm minimization. We know these elements in this vector. All elements of them, they are non-negative because they are signal powers or noise powers. So they are non-negative. So in this way, you can reduce the space of this optimization. Reduce the dimension. And then the first KG elements of the column vector, so are the DOA estimation results. So after opting this estimation result, you can draw this spectrum, draw this squared value of this vector and find the peaks, and then you can find the corresponding DOA estimation results. Now you can reduce, as before, you can reduce the complexity by reducing redundant entries in the covariance matrix as there are repeated covariance lags. So in the covariance matrix, you have repeated lags here, and you can merge them together to have a better estimation for that lag. Also, at the same time, you can reduce the number of variables in the optimization problem. So after reducing these redundancies, so you have the new formulation, a similar one. We just use different symbol. Just use a different symbol to represent this. Use this to represent the new data model. But the same idea. The only thing is that this one and this one, compare them. So we have merged some repeated correlation lags. And then another observation is also only the 0th element in this related to the 0 lag is influenced by noise power. And the estimation of noise power takes up 1 DOF, which can be removed for further complexity reduction. So here, you see this this equation. When you calculate this covariance matrix, you have this is a diagonal. This noise covariance matrix is diagonal. So the off-diagonal entries are 0. So as a result, so you could remove the 0 lag in this RXX. Remove the 0 lag, then you also remove the noise, right? So you can only consider the non-zero lags in this RX before you do this vectorization. So the idea is, we have this, you have removed the redundancy. At the same time, you remove the 0 lag in this formulation so that you don't have noise anymore. So you have a further reduction in the number of variable, further reduction in the computation complexity because the dimension of the problem has been reduced. And we can refer to these, 3 solutions. So first one is Narrowband 1 without any redundancy removal. And then Narrowband 2 is removing redundancy. Narrowband 3, this method is for also removing the 0 lags. So we have 3 solutions based on a single frequency. And then you extend them to the wideband. So wideband signals transformed into multiple frequency bands as described earlier, so we could apply the single frequency algorithms to the frequency range of interest one by one, and then average the results to give the final estimation. So this is not good because I will show you an example later. You see this average can give you a very bad result. A more effective approach that achieves a higher accuracy is to jointly estimate the DOA of the impinging signals across the entire frequency range of interest simultaneously based on the group sparsity concept. So that is, the DOA results corresponding to different frequencies share the same spatial support, although they may have varying power levels. So basically, for each frequency, if there's no signal, then there should be no signal for the other frequency, right? So basically, the share, they have the common support across the frequency range of interest. So that's the observation. So we can use this, apply a group sparsity concept to the whole frequency range. So that's the idea. And so now we assume the frequency range of interest covers Q frequency bands, the DFT domain. And then we construct two matrices, a block diagonal matrix using this, and also a matrix, a data matrix using this individual source vectors. So here is diagonal matrix. This is the individual ones you see here. So you have this individual model for each frequency. Then you can put all ZL into a long vector, and then put this into a diagonal matrix. Also put this into a long vector, right? So this is block diagonal, and instead of, so this here is this one. If you do the vector, so this is a data matrix. So for first frequency being the vector, column vector, second frequency being, and so on. And if you do vectorization of this, that means you have put all the source signals for different frequency bands, into a long vector. So this is a long vector, this is block diagonal times equal to this long vector, right? Basically, still you just use this one. You put all values of L, right? All the L frequency bands together, you get this result. And then we know, so there's group sparsity of different frequencies. So you have the common spatial support. So if that means, okay, if, for example, for the second position of this column vector L0, if there's no signal present in that second position, then there should be no signal for all frequency bands at that same location. Okay, so we can calculate this L21 norm. So basically, we find the row vector, we calculate the L2 norm of this each row vector, and put this L2 norm into a vector, and then we calculate the L1 norm of this new vector. So that's called the L21 norm of this matrix. So here is the L21 norm. So we find the row vector of this. Each row vector we calculate this L2 norm, put them together into a vector, this new vector, and we calculate this L1 norm, right? We minimize this. So this is a way to do this group sparsity, okay? To do this group sparsity, make sure if it's 0, the whole row will be 0. If it's not 0, then the whole row is not 0, okay? So this is the L1 norm group sparsity, and subject to this reconstruction. So this reconstruction error smaller than this epsilon. And again, so we know all the values in this here, they are non-negative. Okay, this will be the formulation for this group sparsity method. So this idea can be applied to extend the other two developed narrowband DOA estimation algorithms to the wideband. So you have this wideband extension. So have narrowband 1, narrowband 2, narrowband 3, and now the extension will be extension 1, extension 2, extension 3. And we also know, okay, the resolution array improves with increased aperture, right? So if you have a larger aperture, then the resolution will improve. You can increase the aperture of array by using more sensors, right? By using more sensors, but you will have a higher cost, right? Higher cost. So the other way to increase the aperture is with the same number of sensors. That means you increase the spacing between adjacent sensors, right? For existing DO estimation method for both narrowband signals and wideband signals, so we normally choose this D smaller or equal to lambda minimum over 2. Lambda minimum is the wavelength corresponding to the highest frequency of the signal. Or it's just, for narrowband case, it's just the frequency of that narrowband signal. Okay, so that's normally we choose this to make sure there's no aliasing for all frequencies of interest. So normally we choose this. But so with this group sparsity concept, actually we can increase this further for the wideband case. So we can increase the spacing D to be larger than this, while still avoiding spatial aliasing in the estimation. Why? This is because the aliasing locations for different frequencies are different. So they have a different frequency. If you have a very large D, then you have an aliasing problem for all the frequencies possibly, right? But the aliasing location, so aliased location, how to say, aliased location will be different for different frequencies. Only the true locations or true locations with the signal are common across the frequencies, right? So that means you have a common, although you can, for each frequency, you have many different possible locations, and there's the aliased ones, but only the common one, the true one, the true directions, they are common across the frequencies of interest. So that means you can increase the D to a larger spacing, you have a good resolution, and still you can avoid the spatial aliasing problem in your estimation. So the group sparsity-based method allows a larger spacing than the standard array, leading to a larger virtual array aperture, and therefore more accurate estimation results can be obtained. And we can expect, however, that when D is larger than some threshold value, the DO estimation results will degrade, as will be shown in our simulation parts. Basically, increase further, although they have the increase further, then there's many aliased locations, there will be will cause interference to your estimation, right? So your estimation performance will start from some point, will degrade. And if you choose the increase D to lambda max over 2, basically, in this case, only the lowest frequency you don't have aliasing problem, but for other frequency you have aliasing problem. Because you have a frequency which has no aliasing, then you can have a good result, still good result, because that part will provide a good reference for the whole frequency range of interest. And you increase this further, there will be resolution will be, in theory, you have a resolution improves, but you have aliasing problem for all frequencies, then they will cause interference. So there's a trade-off. So increase further, then at some point, the gain, will be minimal, and then you have more interference. Then you have the performance will degrade further. Okay, so there's a optimum point for this D. Okay, and we could choose this because in this case, this lowest frequency, there's still no aliasing. Okay, so for the frequency range of interest, there's still one single frequency which has no aliasing problem. So you can expect you have good result. Now simulation and experimental results. We have this m equal to 3, n equal to 5. So it will be 2 times 3, so 6 plus 5 minus 1, it will be 10 sensors. And the sampling frequency Fs is twice the highest frequency of interest. And the normalized frequencies of the impinging signals cover the range from 0.5 pi to pi. And the unit spacing at the start, we choose is to be lambda minimum over 2. Okay, and the number of signal samples in the time domain at each sensor is 128,000, and DFT of 64 points is applied, and then the number of data blocks is 2,000. And there are 15 uncorrelated wideband signals impinging on the array. So we have 10 sensors and 15 uncorrelated signals, so it's underdetermined. And their incident angles are uniformly distributed between this -6 degrees to 60 degrees. And the normalized frequency range of impinging signals cover the frequency band from 17 to 31. So in total, we have 15 bands. And here is the number of entries in vectors matrices for the example. So for this example, basically we have a general equation to calculate the number of variables. So, but for this specific example, you see this is the parameters you need to involved in the optimization. So for this narrowband method, the very original narrowband is a direct vectorization. You have this different number of variables for these vectors, right? This is the source, this is the observed, this is the matrix, this is steering matrix, right? So you see here, this is a very large number, 360,000. Here is only 80,000. So basically 1/4, right? 1/4, 1/5 of the number of variables here. And here is a further reduction. So this is removing redundancy in the covariance matrix. This is further removing the zero lags. And because you can see the running time is 16.4 seconds. Here is 4.6 seconds and 4.1 seconds. This is for one simulation run, okay? And then you do the extension to the wideband case, and you see here, that means almost 1 million, right? Variables in this matrix. And so much smaller again. So 1/4, 1/5 of this number of variables. And the running time is this 2,000 seconds. This is 273 seconds, and further reduction here. So this is for one run. So you think if you do the performance evaluation, then you may run it hundreds of times. That will save you a lot of time by removing the redundancy and removing the zero lags. And also because of this large number of variables to optimize. So by doing this, you can get a better estimation result too. Okay. Basically reduce the dimension of the problem. Okay. Certainly this case, here when you do the optimization, these numbers already. This is known variables, but by reducing them, the dimension of the whole problem will be much smaller. Okay. And here is the DO estimation results obtained by the first method for single frequency. So 15 sources, so it's working. And remove redundancies, still working. So it's matched. So this is a dotted line. This the true locations, and this is estimated. It's blue lines. And removing the noise power, still. So all of them, they are working for single frequency. And then we do the wideband extension. This is the first extension and the second extension and the third extension. So it's clear. So all the sources have been distinguished successfully by this method. Okay. And then you see the performance. So root mean square estimation error versus input SNR for the narrowband case. 500 simulation rounds as average. So you see is narrowband 1, 2, 3, right? This narrowband 1, you see there's a gap between this. So 2, 3, there's not much difference, right? But compared to 1, so basically without removing any redundancy, you see there's still some gap, right? I think it's mainly due to this improvement. Is mainly due to the reduced dimension of the problem. So you can do when you do the optimization, you can get a better estimation result. or the optimization process, have a better optimization process by reducing the dimension of the problem. Here is a wideband. So here you see the improvement is a little bit, but here if you look at the wideband ones have many different frequencies together, this improvement will be much clearer right here. It's a big gap now. But for extension 2 and 3, they are similar, still similar. Now, so the first set of simulation results, you see, okay, all the narrowband ones giving you a good result too, right? So then what's the point of having a wideband method, right? You can use single frequency, it's still working, right? Single frequency. But actually, I can give you another result, okay? So give you an example where the narrowband method clearly fails, while the wideband one can still provide a good result. So what we do, we increase the number of targets to 21, so not 15 anymore. So it's more difficult the problem. So 21, if you do the single frequency estimation, you see you have missed some targets here, right? And the error is also very large. If you do the average for each frequency, 15 frequencies, then you do the average, then you got this result. It's a chaos, right? You can't really see the result, see the directions of the signal. So it's not working if you just have one single frequency when the problem is difficult. However, if you use the wideband method, then you see you can identify these 21 targets clearly, right? So it's a little bit error here, but all of them have been identified successfully. Okay, there's some simulation results. Okay, the next we increase we mentioned, so we can have a larger spacing, right? So here we can use DF. So DF equal to 1, that's a standard one. So lambda minimum over 2, but now we have DF, not choosing DF equal to 1, but 1.33. You see it's working, so there's no aliasing problem, right? So by increasing this D larger than this, you can still identify the sources successfully without having the aliasing problem. And here we choose different values, so 1.0, 1.33, 1.6, and then root mean square error with respect to signal to noise ratio. And you can see when you increase this spacing, you have better result. So a relatively larger unit spacing D corresponding to a larger DF yields more accurate results. Now we draw this curve, so root mean square error estimate results versus DF. So we can increase the DF. Here's DF equal to 1 to standard lambda minimum over 2. Here's 2 is lambda maximum over 2. And here is 3. Okay. Basically, after it's 2, when DF equals 2, the lowest frequency, this is the only frequency without aliasing. All higher frequencies, you have aliasing problem. But for when you increase further to 2, when it's larger than 2, then all frequencies will have aliasing problem. So you can see when you increase this further, still you can distinguish all the sources successfully. That means, okay, as I mentioned, so all of them, they have the true locations of the source. They are the common ones across frequency of interest. Okay, so when you increase further, you can still have successful result. But you increase further, then the results become, it becomes worse and worse. Okay, so this looks like the middle point of this curve, right? The middle point. So in practice, we could choose this lambda max over 2 as the spacing. Okay, because if you increase it further, there's no gain anymore here, right? And purely, you have disadvantage of a large array, right? It will be bulky, large array, you carry it around, it will be more difficult. So, but here too, it seems, you have further and further improvement until you reach this middle point. So this point is a good choice in practice. Here is just the what I mentioned. Okay. To test the performance, so we have also set up a real array system. to test the performance of the developed algorithms. Okay, so to test the performance of the developed algorithms in a real scenario, a co-prime microphone array system with m equal to 2, n equal to 5, that means, okay, you have 8 microphones in total, is set up, and the sampling frequency is 20 kilohertz, band of interest is 5 to 10 kilohertz, and the minimum wavelength is 3.4. So here we still use the standard one. Okay, use the standard spacing. We could increase it further, as shown in the previous simulation. Okay, this is the locations of the sensors, and here is a picture. This is still in my lab. This one we built this long time ago. Okay, you have this power supply, you have this amplifier circuit, and you have these microphones. This is a linear array. This we have previously we have a 20 microphone linear array. We just change the spacing, so now it's a co-prime array. Okay, then you amplify the signal, you connect it to the computer with the PCI board. It's a multi-channel analog digital conversion, so ADC board. So then you can use MATLAB to receive the signal, and then you can test it offline, test the algorithms offline. Okay, so this is the standard this co-prime array with 8 microphones, and this is the result. So you have 10 uncorrelated acoustic source signals distributed between -40 to 50 with approximate step size of 10 degrees, and then you can see that all of them have been identified. Certainly there's a little bit of error. You see here 50 degree, right? There's error here, but roughly, all of them have been identified successfully. Okay, so this is a simulation and the experimental results for this section 3. Now we move to this section 4, is underdetermined wideband DO estimation exploiting frequency diversity. So first is introduction to signal model, and then we talk about wideband DO estimation based on multiple pairs of frequency bands employing group sparsity, and then we have simulation results. Introduction to signal model. Then, so it's clear now that using a physically sparse array, we can increase the DOFs by exploiting the covariance concept, right? However, instead of employing a sparse array, so we don't use a sparse array, we can still do underdetermined DO estimation. So it's possible to extend the covariance concept to different frequencies, where a single URA can be used with 2 continuous wave signals of co-prime frequencies. So basically, so there's but it's still narrowband. So basically, you have to choose 2 signals with co-prime frequencies, and then you can both using the same URA, and then you can form a difference co-array and do underdetermined DO estimation. So still here is still a narrowband scenario. Now this idea can be further extended to the wideband case. A method for wideband DO estimation employing multiple frequency pairs is introduced in this part for this section 4. Basically, we use extended to multiple frequency pairs because it's wideband. Okay, and the key for this method to work is, okay, if you do the cross correlation between different frequency bands and still have a non-zero result, that means what? The signal components, the same signal, so signal components from the same signal but different frequencies, they are correlated, right? If they are not correlated, then you cannot use this method, because if you do cross correlation, you got a 0 result. So the key is to ensure the required correlation characteristics among different frequency components of the received signals, which can be achieved using what? So how can we ensure this? So we can achieve this using, as an example, okay, the linear frequency modulated continuous wave signal as a transmitted waveform. Okay, so here is the standard LFMCW signal with bandwidth B and initial frequency FC. Okay, as a standard formulation of this chirp signal. Okay, so alpha equal to B over T is the chirp rate, and T is the modulation period, and tau is initial time offset, and phi is the initial phase, and mode this is modular operation. Okay, this is a standard signal format. Okay, and then we use a uniform linear array, so it has M sensors. We have K far field targets, and then after reflection, so the echo signals received by this URA, okay, can be expressed in this form. This is a standard, again, this is a standard wideband model. The only difference here, you got this extra part is gamma sub KT. And this is a time varying reflection coefficient owing to target motion or radar cross-section fluctuations. So this is the extra part. So after analog digital conversion with the sampling frequency fs, so each received sensor signal is divided into non-overlapping groups with length L, and the L point DFT is applied. So same as the what we did in section 3. Okay, so basically you have this standard result. P is a block index of the data, and L is a frequency bin index. And so they are the observed signal vector and the noise vector in the frequency domain. So I will not explain this in detail here. Okay, basically DFT, and you have the noise. And then the inter-element spacing D between adjacent physical sensors can be designed according to the frequency interval between adjacent frequency bands. So if you choose this, so just there's a beta to adjust the spacing. So basically, the D can be any spacing you like, but by doing this, we just reduce this to 1 factor beta. And then you substitute this into that formulation, then you will find out the steering vector for frequency bin L is given by this. It's given by this. It's a uniform linear array, okay? And if B equal to 1, then all are integers, right? So L will be integer. Assume that echo signal bandwidth covers Q frequency bins in the DFT domain. And this big phi L represents the set of Q frequency bin indexes. So we select n pairs of frequency bins, with the nth pair consisting of frequency bins Ln1, Ln2. And we first generate a virtual array for the nth frequency pair. So just 1 pair as an example. And based on this Corey concept in the spatial spectral domain, and more DOFs can be provided. And then after this, we can extend this to multiple frequency pairs and use group sparsity. So that's the whole approach. Now in detail, first we calculate the covariance matrix for the two different frequency bands. So Ln1, right? That's the covariance matrix, so autocorrelation matrix for this frequency band Ln1. And then because uncorrelated sources, you have this result. This is the power of the sources at the frequency being Ln1 for target K. Okay, and that's a steering vectors. Okay, and this noise. This is for the second frequency being Ln2, and these values are, because they are power, so signal power. So these values sigma, 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 these 4 values, they are non-negative. Then we can also calculate the cross correlation between this, so Ln1, Ln2, right? And similarly, because cross correlation, the noise, they are not correlated, right? The noise are not correlated, so we don't have the noise term, so we only have the cross correlation for the signal part. So because they are correlated signal, different frequencies of the same signal, they are correlated here because of the signal model. So this is not 0, but it's not non-negative because it's in general, because it's cross correlation, so it's complex valued. Then we do the vectorization for this covariance matrix of this frequency being LN1. So you got the this result. So this is a standard one. This is so you got the array model for this first frequency, and the second one you can also do this vectorization. And then similar to the narrowband case, right, or single frequency case, you have this virtual steering matrix, which is formed by these virtual steering vectors. And each virtual steering vector is a Kronecker product of these two, these corresponding steering vectors, right? The physical steering vectors. There's a real steering vector, and the Kronecker product, you have a virtual steering vector. And then virtual steering vectors for the key targets, you have the virtual steering matrix, okay, for each beam. And because this Rx equal to Rx conjugate Hermitian transpose, so we can use just one of them. Okay, so we vectorize this R, for example, not RxH. We vectorize this Rx. Then, because for this case we don't have noise, right? So we only have the signal part. So this is the cross correlation coefficients, right, in this source vector, virtual source vector, and this is the steering matrix, which is formed by the virtual steering vector, and this virtual steering vector is a Kronecker product of these two individual steering vectors. One is for LN2, one is for LN1. Okay. And so for different combinations of LN1, LN2, different corollaries can be obtained, right? And together they can characterize a large virtual array with positions distributed at the self-difference corollary site and the cross-difference site. So you can form these different values, right? This is a covariance matrix called, right, self-difference corollary. This is cross-difference corollary, okay? And for special case, LN1, LN2 can be chosen to be co-prime. In that case, the signals at the two frequency bands can be considered as signals received by two subarrays of a co-prime array. Okay. Although these three virtual source signals may be different from each other, these vectors share the same spatial support, right? So basically, each row, if you put them into a matrix, then each row you can do the L21 norm for the row vector, right? So now apply the sparsity-based method. We have a search grid of KG, big KG potential incident angles. We can generate these three over-complete steering matrices, okay? And then to use group sparsity, because the three, they have the same support, right? We can have this block diagonal matrix to use this form, this block diagonal matrix here. And then we construct this data matrix. So this data vector for frequency being N1, for frequency being N2, data vector for the cross correlation N1 and N2, between N1 and N2. So you have these three column vectors. This is the source matrix for this pair. And then you can have this Zn, you put all the data, received data, so Zt into this vector Zn, and then you put this is the block diagonal steering matrix, and then this is the, this one is the long vector formed by these three individual vectors, okay? And the plus I, that's the noise part. It's not this I tilde this, okay? You have this definition here given by this. Basically, this is noise part, okay? And then again, you can merge the noise part like a steering matrix for the noise, and merge it with this to form a new steering matrix which covers both signal and noise. And then this is the source part, including noise. And then you can, okay, calculate this L21 norm of this source. It's this source matrix. So minimize the L2 norm, basically minimize. So you find the row vector, calculate the L2 norm, put them into a vector, and minimize this L1 norm. So this is the same as minimizing the L21 norm of this matrix. And then this reconstruction error bound, okay, this is constraint, and you minimize this, then you can find the direction. And to estimate the DOA across the full frequency range of interest, we divided the frequency bands of interest into several pairs, and the group sparsity concept is expanded to all pairs for wideband DOA estimation due to the same spatial support. Okay, for each pair, different pairs, they can form this block diagonal matrix again. So now suppose we have big N pairs, then for each pair, you have this formulation, right? Z and this equation data model equal to this for each pair. And then you can put all this into this block diagonal and put all the data, all this data into this even larger data matrix, right? Big N of them. And then you can put the vectorized data for each pair into a even larger vector, right? And then you can have this, okay, basically this one equal to this, that's a model. And then you do this sparsity-based reconstruction, so minimizes L21 norm of this, minimizes L21 norm of this data matrix. And then subject to this error, reconstruction error smaller than something, and then you can do the estimation. That's a multiple frequency pairs, group sparsity-based method, okay? Now some simulation results. We have 10 sensors is ULA, inter-element spacing D is beta equal to 1, and we have 64 points DFT applied, and number of data blocks is 5,000. And the initial frequency, initial time offset, and initial phase are set to 0, just to simplify the problem, okay? And with the choice of this, so basically we choose all the parameters so that the normalized frequencies of the echo signals cover the range from 0 to 3/8 pi with 12 frequency bands. All the 12 frequency bands are divided into 6 frequency pairs. So the 6 pairs is so 1 and 12, 2 and 11, 3 and 10, 4 and 9, 5, 8, YY 6 and 7. And we have 40 far field targets, okay, with incident angles uniformly distributed between this -6 degrees and 60 degrees. And here are some simulation results. We have one frequency pair, you have multiple, so one frequency pair, you already have a large virtual array, so you can identify the sources successfully. But when you have multiple pairs available, then the estimation result will be better, right? And then if you have this one pair and we increase the number of targets to 60, okay, here is 40, right? So it's okay. They are still both one pair and multiple pairs, they are working, right? But if you increase it to 60, then result for one pair, okay, is not good, right? You have missed a lot of targets, right? And if you do multiple pairs, so this 6 pairs, then you can see you can identify all of them clearly, right? So this is the simulation results. That's for the second part of this recording for section 3 and 4. So in the third part of the recording, this tutorial, I will talk about the remaining parts, section 5, 6, and section 7, the summary.